Welcome to this next video in the playlist on ring theory. In this video what we're going to talk about is the Frobenius endomorphism. Now your first question is probably, what is an endomorphism? Well, a ring endomorphism, to give it its full name, is a special type of ring homomorphism. And it's a ring homomorphism where the domain and codomain ring are exactly the same. So a ring endomorphism is a mapping from a ring into itself, which is a ring homomorphism. Okay, so that's the definition of a ring endomorphism, and don't worry if you haven't fully got that, I'll re-emphasize that later on. The Frobenius endomorphism is a special ring endomorphism that applies for some special rings. Okay, so let me now do the setup, and then I'll show you what the Frobenius endomorphism as a map is actually going to be. Okay, so the Frobenius endomorphism is a special type of ring endomorphism that can be applied to commutative rings which have characteristic equal to a prime natural number. So let me write this down. So we're going to be working with a ring capital R, which first and foremost is a commutative ring. Okay, so we're not interested in non-commutative rings anymore, we're just interested in commutative rings. In addition, I want a commutative ring where the characteristic of the ring is not 0 and it's a natural number that is specifically a prime natural number. Okay, so remember, the prime natural numbers are the things that you called in school just the prime numbers. Okay, 2, 3, 5, 7, 11, 13, 17, and on it goes, 19, etc. Okay, so I'm going to pick then some commutative ring for which the characteristic of that commutative ring is a prime natural number. And I claim that for a commutative ring with characteristic a prime natural number, there exists a Frobenius endomorphism for that ring. Okay, and what I now want to show you is what that Frobenius endomorphism actually is. So the Frobenius endomorphism is going to be a map then, okay, from the ring capital R into itself. Okay, so it's going to carry all the elements of the ring onto themselves, and the way it's specifically going to be defined is it's going to carry any element A, so any little a which is an element of the ring, so I'm just using little a to denote an arbitrary element of the ring. Okay, instead of little r I just prefer a for today. Okay, and I'm going to carry it to a to the power of p, where p is the prime natural number that is the characteristic of this ring. Now, of course, we haven't set p. It could be 2, 3, 5, 7, 11, 13, etc. But for a specific commutative ring where the characteristic of the ring is equal to a prime number, the characteristic will obviously be set. So whichever ring that you are talking about the Frobenius endomorphism for, you find its characteristic, okay, and then you define the Frobenius endomorphism like so. You map all of the elements of the ring onto that element of the ring, multiplied by itself p times. So that's what to the power of p means. It means multiply a by itself p times. So writing this out even more explicitly, I could write this as a times etc., and you multiply a with itself p times. Okay, so you're going to have p lots of a here. And the multiplication here is done in the ring. So you're multiplying a with itself p times in the ring. Okay, and you're mapping every a onto this value, a to the power of p. Okay, so indeed this is a mapping from the ring into itself. When you take any element of the ring, you can do this. You can multiply it by itself p times. That's perfectly well defined, and of course the answer that you get is going to be something that is in the ring. Okay, so true, it is going to take any element here and map it onto another element of the ring. So it's a mapping from the ring onto the ring. The claim is that this is now actually a ring homomorphism. Okay, this map has the special property of being a ring homomorphism, i.e. it obeys additive compatibility, multiplicative compatibility, and the fact that the multiplicative identity in the domain is carried to the multiplicative identity in the codomain. Okay, and that's not obvious yet. We're going to have to discuss why that's going to be true. Okay, and such a ring homomorphism, where the domain and the codomain are the same ring in this way, is then called a ring endomorphism. You can call it a ring homomorphism if you like, and often I probably will just call it a ring homomorphism, but if you like some new specific piece of terminology to show that the domain and the codomain of this ring homomorphism are the same, you can call it a ring endomorphism. So it's another nice big word that you can use to impress people. Okay, so that's why this is called a ring endomorphism, and this specific ring endomorphism is attributed to Frobenius and is therefore called the Frobenius endomorphism. Okay, so there you go, that is the Frobenius endomorphism. So what are we going to spend the rest of the video doing? Well, of course, we're going to spend the rest of the video proving that it is a ring homomorphism, because it isn't trivial that this is a ring homomorphism. Okay, so we're going to prove additive compatibility, which is the least trivial, first, then multiplicative compatibility, which is fairly trivial, and then the fact that the multiplicative identity is carried to the multiplicative identity. The final two you should be able to do instantly, okay, because of the fact that this is a commutative ring. The first one, additive compatibility, is the most difficult, and that's going to require a big argument, and that requires the characteristic of the ring to be a prime, because of course you could define this map for the characteristic of the ring is equal to any natural number. You'd have more difficulty defining it for characteristic of the ring is equal to 0. It would be a very boring mapping in that case. But for any natural number, you could define this mapping, but it wouldn't end up being a ring homomorphism, which is why the Frobenius endomorphism is only defined on the rings that are commutative rings and which specifically have characteristic a prime natural number. That's when you can be sure that this mapping is actually going to be a ring endomorphism. Okay, that's when you can be sure that additive compatibility is actually going to hold. Okay, so let's begin then with trying to prove additive compatibility, and let's see why it's so important that the characteristic of the ring is actually a prime number. Okay, so what do we want to prove then? We want to prove that for all, let's say, A and B that you can possibly dream up from the ring capital R, that it's the case that if you take phi of A plus B, where you've added them together in the ring capital R, okay, so you add A and B together in the domain, okay, and then take phi of the answer, so you add first and then map, that the answer that you get in the codomain here is the same as if you firstly map A into the codomain and map B into the codomain and then add them together in the codomain. And in this case, of course, the addition in the codomain is exactly the same addition as in the domain, because the two rings are exactly the same, so I will drop colouring in the addition. Usually when we're talking about ring homomorphisms, if you watch my previous videos in this playlist, you will be familiar with me colour coding in the additions, but it's not necessary here because the addition is always just in this ring capital R. Okay, so we want to prove that this is true. We don't know this is true, so I'll put a question mark there. We want to prove that it's true. So, how are we going to do this? Well, firstly, let's just explore what both sides are equal to, get a sort of feel for why this isn't so trivial, and then we'll try and prove that it is true. So phi of A plus B, so I've got A and B, which are just arbitrary elements of the ring capital R. I've added them together to get some other element in the ring capital R, and now taking phi of that, so I'll just have to take A plus B here and take it to the power of P. Okay, so that's what the left-hand side is equal to, just by definition. Now let's have a look at the right-hand side here. Well, phi of A is just going to be A to the power of P. Phi of B is just going to be B to the power of P. Okay, so we want to prove that A plus B to the power of P is equal to A to the power of B plus B to the power of P. Now, just from your understanding of classical algebra, you should be thinking, oh, that doesn't look nice. And indeed, it isn't going to be true in a general ring, okay? But if we're talking about a commutative ring which has specifically characteristic equal to P, which is a prime number, then you can say that this is true. Okay, so I'll still put a question mark there. So we need to try and prove that this is equal to this in this commutative ring which has characteristic equal to this prime number P, and it's very important that this is also to the power of P, okay, that these powers are the same as the characteristic which is a prime, okay. So we need to prove this statement. So how are we going to do it? Well, we're going to try and expand the left-hand side here and try and show that it's equal to this. Now, how do we expand this? Well, of course, we apply the binomial expansion. So we're going to have now a little detour into a discussion of the binomial expansion, which is going to be absolutely crucial here. Now, I'm sure you will have seen the binomial expansion at some point before, but you might not have been used to the idea of thinking about it as operating in a general commutative ring. So what I wanted to discuss is the fact that truly you can use the binomial expansion in any general commutative ring. You don't need the characteristic of the ring to be equal to a prime. We'll use that later on. Okay, we're now using the fact that this is a commutative ring to apply the binomial expansion. So I'll just put this here. Okay, so this is a topic worth a video in its own right, but here it's just going to be a little side discussion. So the binomial expansion. Okay, and I'll stress again that this can be used in an arbitrary commutative ring to expand something of this form, a plus b to the power of n. Okay, so the binomial expansion. Okay, so all we need is our arbitrary commutative ring, so I'll just put that here. So it is, we are assuming that it's a commutative ring, and we're now trying to expand this thing a plus b, where they're added together in the ring, and now to the power of something, and we might as well just leave that as to the power of p, keep it in its most immediate form. Okay, right, so how are we going to do this? Well, remember what this just means. Okay, this just means a plus b multiplied by itself p times. So it's a plus b times a plus b times all the way up to the pth a plus b. So you've got p lots of these brackets here, p, a plus b's all multiplied together. Okay, so lots and lots of a plus b's. And of course all these additions and the multiplications in between the brackets are all in the ring capital R. So now we can apply distributivity of multiplication over addition in the arbitrary commutative ring. Okay, so when we actually do this, what we need to do is take something from here, multiply it by something from here, all the way up to taking something here. So we're going to take something from here, times it by something from here, times it from something by here to get one of the parts of this great expansion, and then we're going to have all of those things summed up. Okay, so this is going to be a great sum, so I'll start writing that. So you're going to have a sum here, and of course the addition is going to be in the ring capital R. And now the things that you're going to get are going to be of this form that I continuously keep saying. Something from here times something from here times something from here. Of course, that just comes from distributivity, that what you need to do is take every possible combination of something from here multiplied by something from here multiplied, etc., all the way up to something from here, and then add them all together. Okay, so what then are the things that we're going to be adding together going to look like? Well, of course, in each of these brackets we can only take an a or a b, so we're going to end up with all the things that we're going to have to add together are going to be some power of a times some power of b, and this is where we're using the fact that it's a commutative ring, so we can rearrange the multiplication so that we cluster all the a's together and cluster all the b's together. Okay, so let's say we've got some power of a, and then the power of b will have to be the complementary power, so it will have to be b to the power of p minus i. Okay, so I hope you understand that. If I've got I lots of a, where I will be some natural number from 0 to p, then how many b's am I going to have to have? Well, I'm going to have to pick the rest of them as b's, so I'm going to have p minus i lots of b's. So all the terms are going to look like this that I'm going to get. Okay, and I'll be summing over from I is equal to 0 to p here. Now then the question becomes, well, how many of each of these do I have? Okay, so for instance, if I've got a to the power of 1, b to the power of p minus 1, how many of those do I have? And the answer is I've got quite a few, because I could have taken the a from here and then had all the b's from the other ones, or I could have taken the a from here and then had a b from here and b from all the others. So there are lots of different ways that you could get this same term, and we want to cluster those all together in this great big sum. We don't want to have to consider them all separately. Okay, so what I now want to put in front of this is a multiple of this. Now, this is an important understanding point, that if I've got loads of these, so how many am I actually going to have? Of course, I'm going to have p lots in this case here. Okay, so when I'm taking 1a and p minus 1b's, there are p different ways that I can form that. I can take the a from here, I can take the a from here, all the way up to taking the a from here. So there's p lots of these. So what I would have in my great big sum is p lots of this. I'd have a1 b to the p minus 1 plus a1 b to the p minus 1 plus all the way up to the pth one there. So you'd have overall p of these here. Okay, now what you can do is apply distributivity here. You can factor out the a1 to the times b to the power of p minus 1, and what you'll end up with is 1 plus all the way up to another 1, and you'll have p1s added together there, and then you'll have a1 b to the p minus 1 like so. Okay, so you've now got p1s here. Now, when you have p1s added to it, we call that element, we give that element a symbol, and we give it the same symbol as you would have in the natural numbers. Okay, so that's why you can truly think of all natural numbers as being elements of the ring. Okay, so you can always think, no matter what ring you're dealing with, you can think of 2 as being an element of that ring, because 2 just denotes the multiplicative identity added onto the multiplicative identity. So the multiplicative identity added to itself, well, 2 lots of the multiplicative identity added together. More generally, any natural number p just means 1 added to itself that many times. Okay, so we can denote this like so: p a to the 1 b p minus 1. Okay, so all of that great argument that I've just been through there was just to show you that all of the natural numbers, you can think of them as being inside any ring. They make sense in an arbitrary ring. Okay, so any natural number such as 27 is an element of my ring because it just means 1 plus 1 plus 1 27 times. Okay, so all of the natural numbers can be thought of as being in the arbitrary ring. So that means that in this sum, all I now need to put is a element of the ring, which is the number of times that you have this here, and that will just mean 1 plus 1 plus 1, however many times you have this, and that's why we can think of that as being an element of the ring. So I hope I've got my point there across to you. What I'm about to do is put a binomial coefficient here, which of course you have seen before, but of course you might have asked, well, why is that an element of the ring? Well, now I've explained to you that in an arbitrary ring it just means 1 plus 1 plus 1 that many of times, because of course binomial coefficient will always end up being a natural number. Okay, right, so this is of course going to be the binomial coefficient p choose I, and why is the reason for that? Well, we need to know how many times is this combination of a to the power of I, i.e. how many times are you going to get this particular combination of powers where you've got a to the power of I and b to the power of p minus I. Well, of course, it's just how many different brackets, how many different ways are there of choosing IAs from these p brackets. So you have got p brackets here, and you have to choose IAs. You have to decide which of those brackets you're going to pick the A's from, and we're asking how many different ways are there of doing that, and that will be the number of different ways that you will actually form this, and therefore the number of different times you'll end up having this in the sum here. Okay, so that's where the p choose I comes from, and let me just explore that with you a little bit more by actually reminding you of how the binomial coefficient comes about. Okay, so the binomial coefficient then, the reason it's here is that if we want to ask how many times we're going to get this combination of powers appearing in this great big sum, we need to know how many different ways are there of selecting IAs and p minus IBs. Okay, how many different ways are there of actually picking the brackets from where you're getting the A's and where you're getting the B's. Okay, so to give you an example here, going back to this example actually is probably good. If we're thinking about a to the power of 1, b to the power of p minus 1, you could have picked the a from the first bracket and then b's from all the rest, or you could have picked the a from the second bracket here and b's from all the rest, or a from the third bracket, etc. And those will all be the same combination of powers, but they'll all be separate terms if you were to actually expand this out as a great big sum, and we're bringing those together in this sum here. Okay, more generally, if you've got to pick IAs and the rest are just going to be B's, you're just asking how many different ways are there of picking the brackets that you're going to have these A's from. Okay, well of course for the first A there is P ways of doing that. for the second a that you're picking, there is p minus 1, because you've already used one of them up, and you can't obviously take a from that a second time. And then you continue this on, and it will go down to the ith a that you have to pick. There'll be p minus, and then it will be I minus 1. Okay, if you follow the pattern, for the first one it's p different brackets that you can choose it from. The second one it's p minus 1 different brackets you can choose it from. Following the pattern, the ith one it's going to be p minus I minus 1 different brackets that you can choose it from. Okay, but that isn't actually the number of different ways there are of choosing IAs from these brackets. You see, the reason is that this takes into account the different orders that you could have picked the same brackets, and that's the problem. That's why this isn't finished yet. Okay, so how can I explain that? Can I do it in terms of this example? Okay, the answer is no in that case. I'll have to go to a more complicated example. Let's say we're now talking about a to the power of 2, b to the power of p minus 2 this time. Okay, so here, if I wanted to give you an example, I could have taken the two a's from this bracket, and then taken b's from the rest of them. The problem with this approach is that it would have counted each one of the different ways that I could have chosen a's from these brackets twice, and let me explain why. One of the ways would have been you take your first a from here, and then your second a from here, and then the b's will be all of the rest of them. But the other way is you take your first a from here and your second a from here, and then b's for the rest of them. And the problem with this approach is that that counts them separately, whereas I don't want them to be counted separately. Okay, I don't care what order you actually choose the brackets that you're going to take the a's from. I just care about which brackets of these p brackets have you overall taken the a's from. The problem with this is it not only counts the number of different ways, the number of different choices of brackets that you can have, it also counts all the different ways that you can choose the brackets that are in that combination of brackets, if you get my meaning. Okay, the number of different permutations for how you can select a certain I number of brackets. Okay, so what we have to do then is divide by the number of permutations for how you can select I brackets. So you're picking I brackets. How many different orders are there for how you can pick I brackets? Well, of course, that's I factorial, and this then is the binomial coefficient. So that's just a reminder of why this actually gives you the number of ways of picking I things from P things. Okay, so this will always be a natural number. Okay, whenever you work this out, as long as P and I are natural numbers, which they will be, this will always be a natural number, or except for the fact that I can also equal 0, of course. So a non-negative number is probably the better description. Okay, but you will always end up with a natural number as the answer. You won't end up with 0 as the answer. There's always at least one way of picking it. So that means that all of these are elements in an arbitrary ring, so you can just think of this as multiplication of this element, which just means 1 plus 1 plus 1 however many times with this in the ring. Okay, so this is the binomial expansion then for a plus b to the power of p, and as I say, this works in an arbitrary commutative ring. You do need it to be a commutative ring, because if it's not a commutative ring, it's not fair to say that you can just collect all of the powers of a together and collect all of the powers of b together. Okay, so for instance, these different ways of doing it, picking one a from here and then picking all b's from the other ones, and then then another option is taking the a here and then taking all the b's from the other ones. Those are not necessarily the same thing. Okay, we used commutativity of multiplication to move the a to the front. If we, for instance, took b from here and then a from here and b from all the rest, the a wouldn't be in the front. And if we don't have commutativity, we don't have the right to switch them round. So unless you have commutativity, you don't have the right to say that all of these terms with the same number of a's in and the same number of b's in are actually the same, because they're multiplied in different orders, and only with commutativity can you say that that doesn't matter. Okay, so you do need it to be a commutative ring in order for the binomial expansion to work, but you certainly don't need the characteristic of the commutative ring to be a prime number. Now what we're going to do is we're going to show that if we consider what a plus b to the power of p is in a commutative ring where the characteristic of this ring is equal to this prime p that we are taking a plus b to the power of, that indeed it is actually equal to a to the power of b plus b to, oops, not b, a to the power of p plus b to the power of p. Okay, so why is that going to be the case? Well, all of the other terms in the binomial expansion I claim are going to go to 0. So what we can instantly say is, because this is a commutative ring, we can instantly say that this is, by the binomial expansion, the sum from I is equal to 0 to p of, and now put the binomial coefficient out the front as is more normal, p choose I, a to the power of I, b to the power of p minus I. Okay, so that's perfectly valid. Now, of course, the two extreme terms that we're going to have, if we just expand this for a little bit, let's do I is equal to 0 firstly, then we'll have a to the power of 0 and b to the power of p, so we'd have b to the power of p, and the coefficient we'd have here is p choose 0. How many different ways are there of choosing no a's effectively from p different options? Well, of course, the answer is 1 there, and indeed that fits with our with the actual question here, because we're just going to select b's. We're going to select b from every single bracket, so we're selecting no a's, and there's exactly one way of doing that. So you'll get b to the power of p as your first term. Let's do a little bit more. Okay, so we'll now do I is equal to 1, so we'll then get a to the power of 1, b to the power of p minus 1, and then we'll have p choose 1. How many different ways are there of choosing 1a from p brackets? Well, of course, there's p things there. Okay, and you'll go on, so I'll put plus dot dot dot, and then we'll go up to the most extreme one now, where I is equal to p, so we'll then have a to the p and b to the power of 0, so b's gone now, and then we'll be asking how many ways are there of choosing PA's from P brackets. Well, of course, there's only one way. You pick A from every single one of the brackets. Okay, so this is what it's going to look like, and the claim, obviously, is that only the two extreme terms, the b to the power of the p and the a to the power of p, survive if we're working in a ring of characteristic equal to p. Now, why is that? Well, potentially you can see it here. Remember what this coefficient means. This means, this is the number p, but in the ring that just means 1 plus 1 plus 1 p times. But if we're working in a ring of characteristic equal to p, then that means that 1 plus 1 plus 1 p times is equal to 0. So we're actually multiplying this by 0, so that term's certainly going to go. And in fact, the same thing is going to happen for all of the intermediate terms, because they're all going to have binomial coefficients which are multiples of p. Again, of course, that just means 1 plus 1 plus 1, a multiple of p times, so you can just split it up into those of 1 plus 1 plus 1's p times, and conclude that, of course, 1 plus 1 plus 1, any multiple of p times, is also going to be equal to 0. So my claim is that for I is equal to 1, 2, all the way up to p minus 1, that the binomial coefficient p choose I is a multiple of p, and I can write this as p divides the binomial coefficient p choose I. And that's a problem, because that means that it's equal to 0 effectively in our ring of characteristic p, because as I say, any multiple of p, what is that going to mean? It's going to mean 1 plus 1 plus 1 that many times. But if it's a multiple of p times, then you can just split it up into 1 plus 1 plus 1 p times, and then plus 1 plus 1 plus 1 p times, and then you'll have n lots of those, and of course each one of them is 0, so overall the sum of them is equal to 0. So what I'm trying to say there is that indeed any multiple of p, any natural number which is a multiple of p in this ring of characteristic p, is also going to equal 0. Okay, so all of the coefficients, well, all of the terms in the middle are going to end up being multiplied by 0. These binomial coefficients are going to be equal to 0 in the ring capital R, and therefore they're all going to vanish. So why is it the case then that all the binomial coefficients are going to be multiples of p? Well, you just have to look at this. Okay, remember p is a prime number, and that is important. Okay, that means that if we want to get rid of this p here, okay, which is going to be there as soon as I is greater than 0. Of course, if I is equal to 0, then you're not going to have that p there. The answer is just 1. But as soon as I is equal to 1 or bigger, you are going to have that p there. When I is equal to 1, you'll have just the p there, and then you'll finish. When I is equal to 2, you'll have p times p minus 1, okay, etc. But the point is that as soon as I is greater than 0, you'll have that p in the numerator of this equation, giving the binomial coefficient here. And because it's a prime number, the only thing that you can have in the denominator which would cancel it would be the prime number itself. But of course, for I is equal to 1, 2, all the way up to p minus 1, you're not going to be big enough here to actually get the prime number in here. Okay, only when I is actually equal to p will you actually get the p down here, which will cancel with the p up here, and that's the case where you finally gone to a to the power of p here, of course. Okay, and of course the coefficient goes back to being 1. So indeed all of the intermediate binomial coefficients are going to be multiples of p, because nothing is going to cancel that p. Okay, you might say, well, how can we be sure that this is a natural number? Remember the meaning of this. Of course this is going to be a natural number, so you don't have to worry about it being a natural number. Nothing is going to cancel that p, so you can conclude then that this is a natural number that is a multiple of p, and therefore for all of these ones, 1, 2, all the way up to p minus 1, all the intermediate terms in this binomial expansion, their binomial coefficients is just equal to 0 in the ring of characteristic p, and therefore they vanish. So truly then, when you take a plus b and you take it to the power of p in a ring, commutative ring of characteristic p, then you can instantly say that that is a to the power of p plus b to the power of p, and that's an interesting result in its own right. But now that allows us to conclude that the Frobenius endomorphism is indeed additively compatible. Okay, so indeed we can now conclude that you can either firstly add these two elements a and b together in the domain ring and then take phi of that, or you can firstly map a and b into the under this mapping, okay, and get it in the codomain and then add them together there. The answer is exactly the same. Okay, so we've proven additive compatibility. We'll have a break here whilst you can absorb that great argument, and then in the next video what we'll look at is multiplicative compatibility and the fact that the multiplicative identity is mapped onto the multiplicative identity, and those are a piece of cake compared to additive compatibility.